This video is about if we're at saturation or not, Ksp versus Q. And we've actually already talked about Q earlier in the year when we did equilibrium, but we're going to come back to it. So at this point, you should be able to identify salts as acidic or basic, insoluble or insoluble, write mass-action expressions, which means K equations, and calculate the concentration of ions in soluble and insoluble salts. By the end of the video, you should also be able to tell me which way it might shift. If I added a random amount of solute to the water, is it going to dissolve more? Is it going to dissolve less? Is it going to form a precipitate? Is it going to be saturated? So calculating Q is the exact same way that we calculate K. It's still products or reactants raised to their power, and if you want to skip an icebox, you still keep your coefficient in front. But some of the rules about Q. Remember when we used to do Q before, Q was telling us if you initially put substances in, which way it will shift. And when we used to do it, we said if the Q is less than the K, it has to keep going forward to reach equilibrium. If the Q is more than K, it had to go reverse to undo it, that extra work. And if Q was K, it was at equilibrium, right? Those are the old rules. We're going to apply those same exact rules. We're just going to put new words to them. So again, if Q is less than K, it didn't quite get to equilibrium yet. In this case scenario, when we're talking about insoluble salts, that means it didn't quite dissolve enough yet. And so therefore, we would call that an unsaturated solution and more can dissolve. If Q is equal to Ksp, we used to say that was called equilibrium. In a solution equilibrium, that means it's saturated. That's the key word there. No more will dissolve, no more will precipitate, it's perfect. And if the Q is more than the Ksp, it is supersaturated. We used to say that means the reaction happened too much. In that case of dissolving a salt, that means it dissolved too much, right? And so it became supersaturated and all the extra should precipitate out. So let's try to apply those rules to some calculations. If some unknown substance of XY2 has a Ksp equal to 1 times 10 to the minus 6, and they put a random amount of 0.01 molar X plus 2 and 0.02 molar Y minus 1, is it saturated, will it precipitate, will it dissolve? So because this is a random amount and I don't really know if that's at equilibrium or not, I'm going to use a cube just the way I would have used a K. So XY2 breaks into X plus 2 ions and 2 Y ions that are each negative. And initially, I don't know how much XY2 I have. It doesn't really matter because it's a solid. We're dissolving and we're forming ions. And so we take away from the XY2 to form those ions in a 1 to 2 ratio because there's 1 X and 2 Ys. And at equilibrium, we have an unknown amount minus X. Probably not a lot of shifting there, but X will form X and Y will form 2 X's. And we ignore the white side, the left side. So when on the equilibrium, Q would be equal to X plus 2 times 2Y squared. Also, you could have skipped all that if you remember to keep your coefficient, right? So then what we're going to do is plug those numbers in. X squared is 0.01 and Y squared is 0.02. I don't double it. I'm just saying all of Y is 0.02. Even the 2X is 0.02. I'm going to square it though because that is part of the ratio, right? And if I plug those numbers into my calculator, the Q comes out to be 4 times 10 to the minus 6. Which one's higher, 1 times 10 to the minus 6 or 4 times 10 to the minus 6? Because Q is 4 times bigger than the Ksp, that means that it's supersaturated. It dissolved way more than it should have, and that means any extra will precipitate out. Let's try this again. A little bit trickier this time. A 200 milliliter of 0.004 molar barium chloride is added to 400 milliliters of 0.008 molar potassium sulfate. Will it precipitate form? And they gave us Ksp. Again, it seems that they're adding a random amount of solution, so I know I'm going to be calculating a Q. I'm going to be calculating a Q of something that's insoluble. Not KCl, because KCl is soluble, right? When we double replace, KCl is a strong solid group 1 ions. But instead of the barium sulfate, what we want to know is the barium sulfate going to form a precipitate or not. I know the KCl is not because it's soluble. So in that case, barium, when we form that double replacement, we're saying is barium sulfate going to reionize? I know KCl is going to. So this is the equation. The second equation is what we're running an icebox for. I don't know how much I have of the barium sulfate, but I know it's going to ionize. It's initially 0, but eventually it's going to shift to the right on a 1 to 1 to 1 ratio because there's only one coefficient for each. Again, I don't care about what's on the left side there. Unknowns and not important since solids don't go in our Ks or our Qs. Our Q is going to just be barium times sulfate ions. Here's the problem though, is when you add barium chloride to potassium sulfate, it's no longer just 200 milliliters or just 600 milliliters. Now you have a solution of 800 milliliters. In that case, you've diluted both solutions. So we actually have to do a quick M1 and V1 for both solutions to get their new molarities when they're diluted with one another. So M1 V1 means that we're going to do the first molarity of barium chloride times its solution, and then say the moles will stay the same. I'm just increasing the amount of solution. So now it's now not 200, not 600, but 800 milliliters, and figure out the new barium solution. Same thing here. M1V1 equals M2V2. I actually did V1M1 equals V2M2. Doesn't really matter. So 600 times 0.08 and just changing it to 800. And that gave me the sulfate ion. Now that I've changed them, see what I mean by it was a little trickier. Now that I've changed them, I can plug it into my Q. So that's the only new part, is if they give you the volumes, you're going to have to add them together and fix them up. And then plug them in. If you just plugged them in the way you had it before, it wouldn't be accurate. You would only lose 1 point out of the many points that this question would be worth, though. So it's not a big deal. I plug them in, I multiply them across. The Q came out to be 6 times 10 to the minus 6, and for our last point, we need to go back and compare that to KSP. So again, the Q is way bigger than the KSP because minus 6 is bigger than minus 10. And so again, because the Q is so much bigger than the K, its precipitate is going to form. Questions that might arise is it always going to form a precipitate? No. If we had done the same calculation and the Q came out to be 10 to the minus 20, for example, then we would say, oh, it can dissolve a lot more, right? It's unsaturated. And another question that may arise is, well, what makes Q equal to KSP? Does it have to be exactly 1.1 times 10 to the minus 10? And the answer is, as long as it's like close, like within 1 sig fig, you're probably fine. So if you got 1.2 times 10 to the minus 10, I'd be like, it's about the same. Or 1.0 times 10 to the minus 10, I'd be like, it's about the same as the KSP. It's pretty much saturated, right? If you can't really see by 1 sig fig if they're different, they're probably pretty much the same. Let's try another one. The KSP of silver chloride is 1.6 times 10 to the minus 10th. How many grams of AgCl must be added to a 20 milliliter sample in order for precipitation to occur? So how do we get this white substance to form at the bottom of the solution? So what we're going to do is ionize the Ag and the Cl. We'll know that that is an unknown amount we don't really care about right now, and it forms ions in a 1:1:1 ratio, so there's only one of each part. And then again, we ignore the solid. So it means we could also have just skipped to KSP equals Ag times Cl minus ions if you want. What we're going to do now is put in X's as our ions and plug our KSP in. So notice we're doing this a little backwards, like our last video, and solve for the ion concentration. So my X value came out to be 1.26 times 10 to the minus 20th. But I didn't want to know what the molarity was. I wanted to know how many grams it was. So if you notice, I multiply the molarity by 20 liters. You can also just do this as a molarity formula if you really need to. But molarity times volume gives you moles, right? So I multiply by the 20 liters that they said I had. And I also multiply it by how much AgCl weighs on the reference table so I can know how many grams I have. I know how many moles I have. I need to know how many grams I have. So that AgCl weighs 143.32. And if I multiply across, you can also show this in dimensional analysis or however you need to show it. I got 0.036 grams dissolved. Only 0.036 grams dissolves. So if you put in any other amount, all that extra is going to fall to the bottom as you see in the picture. So it doesn't matter how much you start with, only 0.36 is going to dissolve at that temperature. 0.36, yes? And so that's why we're saying that this unknown value doesn't matter. It doesn't matter how much you pour in. This very tiny amount that you probably can't even measure on our balance is which is dissolving, and no matter how much more you put in, it's falling to the bottom. The KSP of lead-2 fluoride is 4.1 times 10 to the minus 8th. So another one would have gave us a KSP. 4.5 grams of lithium fluoride is added to 4,000 milliliters of water and dissolves completely. That's because lithium is a soluble substance. After addition of how many grams of lead-2 nitrate does the lead-2 fluoride precipitate? So what I might do first is kind of like write out what the heck they're talking about. Lead fluoride is the one that's insoluble and is going to precipitate into dissolve a little bit into lead ions and 2 fluoride ions. And that's the KSP that they gave us. So if we wrote out what's happening, it's going to be some amount which doesn't matter, and the ions, but the ions are a 1:2 ratio, so notice the X and the 2X. And you don't have to write this if you know that the KSP is just going to be lead ions times 2 fluoride ions squared. So you can skip all this if you remember your coefficient in front. What we're going to do is plug our KSP in as 4.1 times 10 to the minus 8th on the left. But what they're saying is they already have some lithium fluoride in the solution. So they already have fluoride in the solution. They already have 4.5 grams in every 4,000 milliliters of fluoride. So what I'm going to do is change that to a molarity instead of grams per milliliter, and plug that in for the amount of fluoride I already have to figure out how much lead I needed. That's what they're asking. How much lead do I need? So 4.5 grams is, if I want to change it to moles, is 25.94 of lithium plus fluorine. And I'm going to divide that by 4 liters as well because it was 4,000 milliliters. And that would give me my molarity of the fluoride that they're talking about. That's going to go in for all the fluorines, the 2 fluorines, but still square it because that's part of your recipe. And I'm going to solve for the lead only. Remember, this 4.1 was given to us as a KSP. So we're saying if there's already fluorine in the water and I want to get it out, how much lead am I adding to pull it out, right? And if I calculate for X, I need to add 2.22 times 10 to the minus 5 molar. I don't like how that looks, so I'm going to fix it real quick so you can see it better. There you go. And if I wanted to know how many grams that is, right now it's a molarity. So I multiply it by its liters again, 4 liters, and I multiply it by its molar mass. 331 is how much the lead nitrate weighs, and that's how much lead nitrate I would have to add, 0.029 grams. So we're basically talking about like purifying water and making precipitates, pulling things out so we can filter it out. At this point, you should be able to determine the shift of the equilibrium and also know how to calculate KSPs for any given insoluble salt.